So we've been looking at measuring heat. There are challenges that are associated with this, and the most glaring one is the heat loss to the surrounding. So whenever you're measuring heat, there's always going to be heat loss to the surrounding. This heat, unfortunately, it's hard to measure how much heat was lost to the surrounding. So we just have to live with this problem, okay? Whenever you do an experiment that is measuring heat, you always know there will be some heat lost to the surrounding. If, for instance, you are doing a calorimetry experiment and you have a beaker, and your beaker has water, and maybe you have a spirit lamp heating up that water, something people don't realize is that the beaker itself is part of the surrounding. There is some heat that is lost to heat up the beaker, and we need to be able to quantify that. To be able to quantify that, we look at the difference between heat capacity and specific heat capacity. Specific heat capacity is what you're used to. It's the C in Q equal mc delta T. So this is specific heat capacity. It tells you how much energy you need to raise 1 gram of substance by 1 degree Celsius or 1 Kelvin. Okay, that's specific heat capacity. It's per gram. Now, heat capacity, on the other hand, is not per gram. It's per however many grams you have in that substance. Q in this case would be C, which is heat capacity, times delta T. Because the C here already encompasses M and C. Okay, so heat capacity is basically specific heat capacity times the mass of the object that you have. So if I have a 250 ml beaker made of silicon dioxide, and I have a 1000 ml beaker made of silicon dioxide, same material, they will have the same specific heat capacity, but they would have different heat capacity. So whenever we're doing calculations for how much heat is produced by a reaction, we should know that some of the heat goes into warming up or cooling down the container that we're using. In IB, we don't usually do this, include this in the calculation, but there is a simulation that I have attached that you can use to figure out how to do these calculations, where you are including the heat capacity of the container or the amount of heat that has been absorbed or released from the container itself. Okay, but just know, for IB, we do not usually care about this. We don't care about it when we do the calculations, but if you are evaluating a process, you can use this as a source of error. So to sort of help with this problem that we have with heat loss to the surrounding, usually when we collect data, let's say you mix two liquids, and the liquids, they initially both have maybe 25 degrees Celsius, say. They are 25 degrees Celsius, and then as soon as you mix them together, their temperature increases, but then at some point it's going to start to go down, and you want to allow it to go down for some time before stopping the process. We want to find delta T, so the change in temperature, but because there's heat loss to the surrounding, people in chemistry have decided to use a technique where they extrapolate the value of T final. And the way that we do that is we create a tangent line that extrapolates all the way to the initial temperature. So you draw a line from this point. Oops. This is not straight. There we go. You draw a line that coincides with the point at which you added the two substances and the temperature started to increase, and the tangent line that we have over here, and then our T final is going to be where these 2 points intersect. Note that if we had not extrapolated, so what we did in 10th grade, for instance, we just looked for the highest temperature that we reached, and we said that was our T final in 10th grade. In 11th grade and 12th grade, we are upping our game, so we are using this technique of extrapolating to find the final temperature. The reason we do this is we know that there's heat loss to the surrounding, so that affects the highest temperature that reached by the solution. So we extrapolate to sort of estimate where it would have been had we not had heat loss to the surrounding. You will find as you do your calculations that even if you do this, you will still be way off the true value that is published. But at least this is a way that we start to solve this problem.